part 4 of chapter 7, looking at pulleys now. How pulleys kind of change the directions of forces. That's like a simple machine. Alright, block B drags block A across a frictionless table as it falls. The string and the pulley are both massless. That's a simplifying approximation here. There is no friction where the pulley turns on its axle. Again, that's a simplifying approximation. Therefore, the tension of block A on the string is equal to the tension of block B on the string. Alright, at least that's true as far as their magnitudes are concerned. That is true. Okay, so if we look at these two things, this is the tension of the string on block A. This is the tension of the string on block B, and they are equal. So what it's saying is that because of the simplifying approximations about the massless string and pulley and all that, you can say this is like the tension of block B on A and the tension of block A on B acting as if they are an action-reaction pair. Since the tension of A on B equals the tension of B on A, we can draw the simplified free body diagram on the right below. Forces the tension of A on B and tension of B on A act as if they are in an action-reaction pair, even though they are not. Opposite in direction because the tension force gets turned by the pulley. Okay. Keep going. Quick check 7.7. All three 50-kilogram blocks are at rest. The tension in rope 2 is what compared to the tension in rope 1? Pause it and think about it. Again, we may want to think kind of just automatically, well, there's two 50-kilogram things pulling this this string, so it's got to be higher in rope 2, but it's not, because same reason that about the student pulling the rope against the wall versus two students pulling. 50-kilogram pulling here is going to equal the same amount of force that the ceiling is pulling on that string as well. So it's going to do the same amount of work as that other 50-kilogram block. So they should be equal. And they are. All right. Quick check 7.8. The two masses are at rest. The pulleys are frictionless. The scale is in kilograms. What does the scale read? Pause and think about it. Again, you might think 10, but that's not it. This would be it's going to read 5 for the same reason as if this string were, if you were just holding this scale, or if the scale was attached to a wall or a ceiling or something, it would be the same situation. So it's going to read 5. It's reading the tension in the string. All right, quick check 7.9. The acceleration constraint here is what? What is the acceleration constraint going to be here? Comparing the acceleration of block B in the y direction and the acceleration of block A in the y direction. Pause it and think about it. All right, so we know block A has a higher mass than block B, so we know that the acceleration is going to go this way. In other words, block A is going to accelerate down, block B is going to accelerate up. So they will have the exact same magnitude of acceleration, but because block A is accelerating downward, we would call that a negative acceleration. And block B is accelerating upward, we call that a positive acceleration. So they should be equal but opposite in sign. So I would like to say, let's see, acceleration of A in the y is equal to the negative acceleration of B in the y. So certainly C or D look the same, so I'm going to say choice E. Yep. Okay. Working with ropes and pulleys, here's a little tactics box. For massless ropes or strings and massless frictionless pulleys, if a force pulls on one end of a rope, the tension in the rope equals the magnitude of the pulling force. If two objects are connected by a rope, the tension is the same at both ends. If the rope passes over a pulley, the tension in the rope is unaffected. Okay, some things to keep in mind. Quick check 7.10. The top block is accelerated across a frictionless table by the falling mass little m. The string is massless and the pulley is both massless and frictionless. The tension in the string is going to be what? Let's think about that. This actually won't be very hard if you just think about one thing here. Let me get it where I can write on it. Okay. Look at this little m right here. This is just little m. What are the forces on it? We have the tension in the string. We have the force of gravity, which is just little mg. All right, we know that the acceleration is because this guy is accelerating across that frictionless table, then this guy has to be accelerating downward. That's the acceleration constraint that we have here. So that being the case, the tension in the string must be less than mg. So I'm going to say choice A. And let's go back to the PowerPoint now. And that is right. Okay, keep on going. Quick check 7.11. Block A is accelerated across a frictionless table. The string is massless and the pulley is both massless and frictionless, which is true. Alright, let's pause and think about it if you want to. Choice A, let's look at it. Block A accelerates faster in case A than in case B. Alright, so what this is saying is this block, the second block down here, has a weight of 10 newtons. So it is able to, the gravitational force on this thing is 10 newtons. Alright. Whereas in case B, there is a 10 Newton tension in that rope. Well, we've already determined the gravitational force, the tension in the rope is, in this case, must be less than the weight of this block because it's accelerating downward. So the weight of the block has to be greater than the tension force in the rope. So the tension force in the rope here is less than 10 newtons. Whereas in case B, the tension in this rope is 10 newtons. So this is less than 10 newtons of tension. This is more than this is 10 newtons of tension. So we're going to say block A has to accelerate faster in case B than in case A. So that looks like choice C. All right, I hope you're kind of getting a feel. I know this, it's every time we encounter new issues in these physics chapters, it's a little bit what's the word? It's a little bit maybe disheartening or discouraging at first because it doesn't match what our brains intuitively think, but that's the point of the class. So hopefully you're appreciating that we are that our minds are getting challenged and getting trained to think like a physicist instead of like just an average Joe on the street. So, and also, the more we do these problems and practice it, the better we get at it, and the more our brains will adapt to that knowledge. So, we have some summary slides. Certainly, if you want to look through these summary slides, feel free to. Pause it if you want to read any of these. And remember what was said. And that is the end of Chapter 7 lecture. Good luck on Chapter 7 homework. Go ahead and get on it. And if you have trouble on a particular problem, feel free to text me about that, and maybe I can make a video about that particular problem. See you in class next time.